into this section here on the law of cosines. We looked at a couple of examples, one where we had two sides in the included angle of an oblique triangle and we solved it, one where we had the three sides of an oblique triangle and we solved it. Now we'll show how we can use the law of cosines to help us with applications, and from the law of cosines is derived a formula called Heron's formula, or sometimes called Heron's formula, which allows you to find the area of a triangle if you just know the lengths of the three sides. So we'll look at that as well. But first things first, let's try an application, and we'll do one with where we're looking at measurements using bearing. It says here in this first example, a Coast Guard ship on a routine training run leaves its base at 18 miles per hour on a course of north 17 degrees east, that's its bearing. 3 hours later, a distress call comes in from a cargo ship that's located 180 miles from base and is at a bearing of north 48 degrees east. And we're to determine two things. First, we're going to find out how far is the Coast Guard ship from the cargo ship, and that's assuming when it, talking about when it receives the distress call. And we're going to round it to the nearest tenth of a mile. We'll look at the second part in just a minute here. I'm going to try, well, maybe I better use a yardstick here, and I'm going to try to draw this out if I can a little bit. Now pretty much everything's up here in the first quadrant because of the bearings that are given, so I'm going to draw my drawing that way. I'm going to put most of the emphasis here in the first quadrant, and we'll say that the origin right here is the base. The base that the Coast Guard is leaving here, and it goes 18 miles an hour for 3 hours, so that's 18 times 3, that's 54 miles at a course of north, this would be north up this way, 17 degrees towards the east. So 17 degrees, I'm going to kind of eyeball this best I can, and I'm going to approximate 17 degrees to be about like this. This is not perfect by any means, but I'm going to try to approximate it so it's something along those lines. Here, we'll do this. And we'll say that this angle here is 17 degrees. That's from this bearing right here, 17 degrees. So now, if we go travel 54 miles, here, maybe make this a little shorter here, 54 miles being the distance here, and then it says they get a distress call. This is the Coast Guard ship here, I'll put CG next to it. And then they get a distress call from a cargo ship that's 180 miles away at a bearing of north 48 east, so that's a little bit further towards the east and a little bit further away from the base. So maybe something, well, maybe a little bit more here. Try to make it as close as I can, eyeballing it. There we go. And what we'll say here now is that this distance here, let's make it a little bit shorter here so that we can squeeze everything in here. I'll just kind of fudge this just a little bit. Here's my Coast Guard. And we'll bring this back just a little bit, and we'll say that this is my cargo ship. And that this distance here is 180. This is in miles. Here, let me put miles next to it. So this is 54 miles. You can see me. 54 miles, and then this is 180 miles. I'm not drawing the scale, as you can tell. Try to get it close. And we want to know how far apart the Coast Guard is from the cargo ship. So what we want here, and I'll use a different color pen, you make a halfway decent drawing, you get probably a much better idea of what's going on with the problem here. So I want this distance here, and I'll do this in blue. Okay, and I'll call that, for lack of a better name, I'll call that distance x. Well, oh, and by the way, we know that this distance here is 48 degrees. 48 degrees from that bearing. So what I need here is to find x. I have two of the sides. I have 54 here and I have 180 here. I need the included angle so I can find that opposite side. I need this angle right here. which I'm going to mark in blue as well. Well, I can figure that out. All the way over here is 48. This part here is 17. So the angle in question would be 48 degrees minus 17 degrees, or 31 degrees. So that's that guy right there. And now I can use the law of cosines and figure this out. X squared is equal to 54 squared plus 180 squared minus 2 times 54 times 180 times the cosine of 31 degrees. Now I hope that you can see that. My triangle is drawn here with 2 sides in black ink and 1 side in blue. I'm trying to find the side that's in blue ink, which I do not know. I'm going to call it X. And this included angle down here I can determine from these 2 bearings. That this turns out to be the difference in the 2, or 31 degrees. So now I got to get my calculator. Hopefully I left it here. I did. And let's clear out this stuff. Let's do 54 squared plus 180 squared minus, let's see, this would be 2 times 54, that'd be 108 times 180 times the cosine of 31 degrees. And hopefully, if I hold that up, that kind of looks like that makes sense. And I hit enter, and I get that x squared. I'll just lean it up against me, so hopefully it's still there. X squared equals 18,652.66767. So if I take the square root of both sides, and I raise this to the 0.5 power, and I get x is approximately 136.5747. That's close enough. And we're going to round this to the nearest tenth of a mile. So to the nearest tenth of a mile would be 136.6. So it's a story problem. It's an application. I'm going to write out my answer here. Let me put the calculator up. And I have that the Coast Guard, capital C, Coast Guard ship is 136.6 miles from the cargo ship. And there's my answer to the first part. Now my answer to the second part, I'm going to have to get my yardstick again, if I'm not mistaken, and set some up here. It says, what bearing should the Coast Guard ship follow to reach the cargo ship? So from here, what bearing to go from here to here? Well, notice that this is not at the origin. I'm going to set this up with north, south, east, west. So I'm going to grab my yardstick again. This time I think I'll just kind of put dotted, if that'll make it a little bit easier. Hopefully it will. A dotted set of axes that now go through this point here where the Coast Guard ship is. And let's see. Okay. So now I can use these to figure out my north, south, east, and west. So from here, apparently, to go from here to the cargo ship, I'm going a little bit east of due north. So I'm going to get my bearing. I need this angle right here. Okay, that's the angle I need. Let's see, what do I have? I have this angle back here, and I'm trying to find the angle in question there. I'm thinking maybe what I'll do is I'll see if I can find this angle right here. Let me get a different color pen, as the blue is already being used a little bit. So let's try pink pen here. I'm going to try to find this angle right here, which I'm going to call theta. Now I have all 3 sides because I know that x is 136.6 approximately. So, and this is also in miles. So if I use the version of the law of cosines where I have the three sides, I'm trying to find the angle. I really didn't give myself much space. I thought I was going to need more space here. Let's give it a shot. I'm going to say that the cosine of theta, that's this angle here. These are the two sides that include the angle, so that would be 54 squared plus 136.6 squared. Probably would take that out a few more places, and I think I will when I punch it into my calculator, minus 180 squared all over 2 times 54 times 136.6. Again, I'll probably take that a little bit further. So let's see if I can figure that out. Let me grab my calculator. And I have 54 squared plus, what is that, 136.57477 squared minus 180 squared, and I'm going to divide that by, looks like the product here of 2 times 54, that's 108, times that long version of that number here, 136.57477, and I hit that and I get a negative number, which kind of makes sense because that angle looks like it's going to be bigger than 90 degrees. It looks like it's going to be obtuse. So I get negative 0.73432. So now I'm going to take the inverse cosine of this to figure out what theta is. Well, theta would be, let's see, inverse cosine, grab that calculator, negative 0.73432, and I get 137.249. 137.2497882, or to the nearest tenth, just barely to the nearest tenth. You round down to 137.2. Now they didn't ask for the angle. No, they did ask for the angle to be to the nearest tenth of a degree. So 137.2 degrees. Now that's not my answer. That's the pink angle there. That's theta. The angle that I need is this angle with the dotted arc. But would you agree, and I hope that you will, if I know this angle, now I'll use this blue color here, if I know this angle here, these two angles are supplementary. They would add up to 180 because they are adjacent angles with the same vertex whose exterior sides form a line. So they're supplementary. Now I do know that theta is 137.2, but what about this little guy right here? What about him? Well, these two lines are vertical, and I have a third line here, that, or line segment, that intersects them like a transversal. So I think you'll agree that this angle here, this little guy in blue, and this angle down here, which is 17 degrees, they would be alternate interiors. Therefore, they would be congruent. So if this guy here is 17, this guy here is 17. So the angle in question here, with the heavy blue arc, that would be 137.2 minus 17. And this is in degrees. So that would be 120.2 degrees. And since these two guys are supplementary, 180 minus 120.2 degrees would be 59.8 degrees. So this angle right here, the one with the dotted black ink there, that's going to be 58 or 59.8 degrees. Well, that's going to be what we need for our bearing because it's that many degrees east from due north. So let's see, what bearing should the Coast Guard ship follow? The Coast Guard, hopefully you can see this, ship should follow a bearing of north 59.8 degrees east to reach the cargo ship. We have to erase a little bit of this. I'm kind of going into the other half of the board. So I use the law of cosines to help me to find the missing measure and to help me to find the missing angle, or to help me find the information to find the missing angle, and that answers that problem. That's just one kind of application, but it's a good one, and notice how important the drawing was. And if you tried to make this drawing really small on a piece of paper, it'd be difficult to get everything labeled, and you might end up making a mistake because of trying to squeeze it into a small space. You know, get a piece of scratch paper and draw it out properly so that as you're solving the problem, you have no trouble identifying the missing parts or the parts that you're solving for. Alright, now, there's an application, one of many types, but we're going to jump over to here. Now, Heron's formula, or Hero's formula, is used when you know the three sides of a triangle, and that's all you know. You don't know if you have a right angle so that you can use the legs, the space and height. You don't have any of the angles so that you can't use the formula from that we discussed in the last section, 1/2 AB sine C. So we are going to use this formula here. It says, given a triangle with sides of lengths A, B, and C, the area is given to be area equals the square root of S times the quantity S minus A times the quantity S minus B times the quantity S minus C, A, B, and C being those sides, where S is equal to A plus B plus C divided by 2. So this is a little different, but the nice thing is you don't have to have any of the angles, you don't have to have the height. You can find it if you just know the three sides. And you can see why this is going to go around along with this section, because we're looking at solving triangles where we know the three sides. So I'm going to go ahead and do an example here. It says find the area of a triangle with sides of length 15.4 meters, 22.6 meters, and C equal to 26 meters. We're going to round to the nearest square meter. Well, A is here, A is 15.4. I'm going to drop the units for just a second. B is 22.6, C is 26. So I'm going to find S first by adding 15.4 plus 22.6 plus 26 and dividing by 2. Well, 15.4 and 22.6 would give me 38. 38 and 26 is 38 and 26, 64. Divided by 2 is 32. I'm going to plug 32 in for S now. I get the area to be equal to the square root of 32, that's the S, times the quantity 32 minus A, which was 15.4, times 32 minus B, which is 22.6. I'm going to have to extend my vinculum there for my radical sign, and then times S minus C, which would be, well, not S, which would be 32 minus C, which is 26. Okay? So this is the square root of 32 times, looks like 16.6 times 9.4 times 6. Time to get the calculator again. So I put the calculator to work here. I'm going to multiply 32 times 16.6 times 9.4 times 6, and then I'm going to take the square root of this. Well, that's a bigger number than I was expecting here. Yeah, I guess so. And then I'm going to take the square root of this. So I'm going to raise this to the 0.5 power, and I get 173.088. 173.088. 173.088. And we are rounding, in this case, to the nearest square meter. So the area of the triangle, and our units were in meters, so our area to the nearest whole amount, nearest square meter, would be is 173 square meters. And I write out the answer there. just like I wrote out the answers to the other one. All right. Now, this is a fairly useful formula. This is something that you could most definitely see on like an ACT or an SAT test, so it'd be a good one to put to memory. And of course the law of sines and the law of cosines and SOHCAHTOA for solving triangles. Really, really important. Lots and lots and lots of applications. So be sure to practice, practice, practice. This actually finishes up the last section of pure trig that we're going to cover in this course. We are going to do some more stuff with trig, but this is the last section of just pure information given with respect to trigonometry. So I hope you enjoyed it, because trigonometry, if you're studying math for a while in high school and in college, it doesn't go away. It's going to be with you for a little bit. So make sure that you practice, practice, practice.